Uh, so let me introduce our speaker for today, and I'll do it, really briefly. Several of you came for Valerio Lucarini's talk last week, and this is kind of in the same problem domain, is the way I would put it. So the speaker today is Justin Finkel, who comes from the University of Chicago. His undergraduate degree was in physics and mathematics from Washington University in St. Louis. Then he ended up at Chicago. I did a PhD in computational and applied mathematics. Then he ended up at MIT in Paul Gorman's group working on climate extremes. And now he's back at Chicago. And the idea is that if we are successful in convincing him and people here, he ends up here. So that's kind of the context of all of this. So, there are not that many people who work in the mathematics and physics framework also interested in looking at applications of their work. And so that's where I think it's really interesting to have Justin here. And especially in complex adaptive systems, Manfred is here for that because this is a very eclectic group. And so there's a welcoming environment for people who are willing to engage with a variety of people. And so that's kind of the context. So for today, actually one more thing before that. So the reason we, in our research group, we got particularly excited talking to him is we are trying to work on what we call weather jiu-jitsu, which is how do you perturb extreme events that are happening in nature so that we can avert them. When Justin first wrote to me, he was working on how do you boost extremes in climate models so that in the future, if you can understand what could be even more extreme events that occur. And my first reaction was, okay, but you're trying to prove this as a point perhaps, or what are you doing? And then we realized, or at least I realized, that it was the same game mathematically in some sense. And so we are now going to try to destroy the world in every possible way. So with that, let me turn it over to you and introduce today's talk.
Thanks so much, Manu, for having me here, for inviting me, and for assembling the crowd, and for Corey for setting everything up. As Manu said, I'm excited to be visiting, to be talking to a crowd with diverse backgrounds, and to that end, I want to bring everyone along and have everyone be on the same page. So feel free to stop me with clarifying or critical or any questions along the way. You can keep it casual. So that being said. Manu introduced my background, so I'll just get into it. This talk is I labeled it Try Early, Emulate, some specific considerations that I've come across in my research in the last few years on computational methods for better simulating, sampling, understanding, maybe eventually controlling extreme weather events. And a lot of this will be work presented from my time at MIT. But yes, right now I'm back at UChicago and continuing this stuff. So when I think of extreme weather events, what attracts me to it is I think it's a whetstone, a place to hone a lot of tools that we have in computational science and engineering. It brings out the really hardest aspects of a lot of problems. The particular, and they're very high impact, obviously. In particular, I can point to several examples like the 2010 Pakistan floods, very devastating, dropped rain just really persistently across Pakistan and left farmers camping next to their fields like this. Very different kind of event in different part of the world. Cold air outbreaks. I'm a little bit more used to these in the mid latitudes, related to meanderings of the stratospheric polar vortex, which I spent my PhD on. But big cold air outbreaks where Arctic air gets unleashed over the broader span. And then related to the same phenomenon, down south, Australian heat waves and bushfires. These are also linked to the polar vortex. And all of these have different levels of disastrous impact, obviously. But I guess the common thread in the way that we try to address all of these proceeds with several tools. Like for a long time, we seek to mitigate the impacts on this by short-term weather forecasting. If we can improve the skill at which we forecast these events, we can help people prepare in the near term to evacuate or to take whatever short-term measures. But then there's related to this longer-term problem of how do we assess the statistics of these events in the long term, the climatology, so to say. Even in a stationary climate, this is an important question because there's some kind of risk whenever unusual events happen, they sort of catch us off guard. But climate change amplifies the problem. And these work in a feedback loop with the same types of models. And the way I fit into this, I think, is taking some ideas from applied mathematics and algorithms to help simulate the extremes better, more efficiently, faster, more informatively. And again, thinking ultimately about moving beyond just estimating the system and using our knowledge to apply controls. So this is how I see my research fitting in. And so here's a general overview of the talk. First, I'll talk about the sort of general challenge of why extremes are hard to compute and estimate, et cetera, and a sort of generic strategy to approach them. Then I'll talk about specific challenges I've come across when attacking specific kinds of extremes like precipitation events as opposed to others, like Valerio talked about a couple of weeks ago, other kinds of events. Oops. I'll talk about the role of model hierarchies, which we make, from toy models to really realistic models that we make heavy use of in climate science. And then eventually, at the end, talk about using modern AI technologies, et cetera, to accelerate all of this research. All right, so first of all, fundamentally, the statistics of extreme weather events, I think I cut off a little. The statistics of extreme weather events are all just very difficult to estimate by their very nature of being extreme. And I'll say direct to estimate with direct numerical sampling. So if you imagine you have a biased coin, say it has a 1% chance of landing heads, this is a basic statistical reason, but we don't know this probability a priori. We want to estimate it by doing experiments. You take the coin and you flip it over and over again, and you count how many heads land. So if you flip it 100 times, sort of an expensive experiment, on average, you would expect to get one head, right? But if you calculate probabilities, you're also very likely to get 0 heads, and you're also almost like half as likely to get 2 heads. So there's a huge potential for a huge relative uncertainty of 100% in either direction. And if you think instead of flipping a coin of running a climate model forward, like an expensive coupled model that simulates the atmospheres and the oceans and the cryosphere and whatever, these could be 2 sample realizations from that time series. One of them would give you 2 events in a century, and the other would give you 0. And these are expensive to run. So every coin flip is a lot of expense, and we would need to run for like 10,000 years to get a reasonable estimate. So that's the fundamental statistical challenge. And the general approach that I'll talk about, one general approach, is rare event algorithms. It's a way of running climate models deliberately, steering them, applying kicks to make the extremes happen more often. And then crucially, you have to correct for that statistical bias you've introduced by these nudges. And I'll get more into these details later. But yes, this is the fundamental issue. And I'll just point out, I apologize that this acronym DNS, which I'll be using for direct numerical sampling, meaning just running a climate model forward and collecting events, this clashes with the turbulence literature, which uses DNS to mean running a turbulence without parameterization. But here I mean this. Okay. So any questions so far? Okay. So there's several alternative approaches to this direct numerical sampling, which is inefficient. One is statistical approaches like extreme value theory. So this is a theory for how the asymptotic behavior of probability distributions look in the tail when you consider the maximum of something. And it's a very elegant theory, and with enough data, you can estimate probabilities of this form. So given any kind of observable, there might be some tail you estimate. But there's limitations to this. It doesn't provide physical realizations of the event. I could say, okay, X is the rainfall over some region. Okay, so it's a number, but it doesn't come close to capturing the complex spatiotemporal interactions involved with a big flooding event like this. To really understand and prepare for these, we need to have a full dynamical picture of the events leading up to it, how the water vapor and the winds were co-arranged in the atmosphere to drive this event. To get a better sense of these so-called storylines. And that brings me to the second approach, which is called ensemble boosting, which is an interesting set of methods which has been developed in recent years at ETH Zurich largely, which is to generate these physical realizations. as follows. Say you have a run of a climate model, which is the solid black line, or sorry, solid red line. And you identify within it some extreme events that happened, like a precipitation spike. Okay, so we ask the question, how much worse could this event have been, if only for a little butterfly fly flap somewhere? And so if you go back in time, you save the simulation, you go back in time before the event happened, and you apply tiny little round-off errors to the model, and you rerun it forward. Because of chaotic dynamics in the atmosphere, you get a divergence of possibilities, and you get some events which become even more extreme. So, never let a good disaster go to waste. Just go back in time and see what could have happened so that you can maybe get a sense of even worse future disasters. And from this you can get detailed spatiotemporal fields, etc. So this is really nice. The downside is it doesn't directly give us probabilities. It just gives us these storylines, things that could have happened. So between these two approaches, the one that I'll be following is rare event sampling, which tries to get the best of both worlds, both the physical storylines and probabilities attached to them. So to illustrate how this works, let's say that our simulation consists of some state vector, x of t, which could be all the wind speeds, temperatures, pressures, humidities, etc. Everything you need to specify the evolution of an atmospheric model or an ocean model. And then r of x of t is some functional of interest that quantifies the disaster of the event, like the rainfall over a specific location. We want to get the extremes of that. So we start by running initially a straightforward DNS. And so we could run this for a long time and then cut it into chunks, or we could run each of these chunks in parallel. The point is, each of these 4 chunks is an independent initial ensemble that we can use to estimate. So what do? I want to estimate the tail, the probability of reaching very high. So I rank these ensemble members, and I draw a threshold that only half of them exceed. And I call that threshold L1. And by construction, the probability of exceeding it is 1/2, right? And now I want to focus on the extreme half of this ensemble. So I take those members which did exceed the threshold, and I apply small perturbations to them at the point where they cross the threshold, and I see how much worse the event could have been, or how different the event could have been. And just with the small perturbation, I get I now replenish the population to a size of 4, but now all of them are at least some level of extreme. And I call these descendants and ancestors. So think of this as like a genetic algorithm. And then I once again rank the 4 ensemble members and kill the least interesting, the least extreme half. And then I do it again. I apply small perturbations to the survivors. And I generate new possibilities. And I keep ranking, and then killing, and then cloning, and then killing, and then cloning. And you proceed in this iterative sequence. At each level, you estimate some conditional exceedance probability. The probability of exceeding L2, given that you exceed L1, is 1/2, etc. And ultimately, the probability of exceeding this very high level that you've reached to is 1/2 raised to the 4th, or 1/16, which is a much smaller probability, but most importantly, we got this from only running 12 simulations. If you just ran 12 simulations straightforwardly, you could only estimate probabilities of 1 in 12. But by deliberately allocating the computation towards the tails, we can estimate a probability of 1 in 16. So that theoretically is a speed up, and that's what we're going for, to just design the experiments more efficiently. Any questions about that basic picture? Okay, so this idea came out, has a long history. This specific algorithm has a name of adaptive multi-level splitting, or AMS. And there are other related algorithms that initially came from physics and have been applied to molecular dynamics and other fields. The first time this made an impact in climate science was a similar, not quite the same algorithm that worked for sampling hot seasons. So this research group in France, they ran ensembles of summers in the community Earth system model. And what the red line is showing just a controlled simulation, a DNS. All these blue lines are showing what they get with the algorithm. They find much hotter possible summers. Okay, so that's pretty cool. And inspired by this, I asked, together with my postdoc advisor Paul O'Gorman, can we make AMS or a similar algorithm work on precipitation events? That was our initial goal in a global climate model. It would be a new application. So that's what we set out to do. And that's when we ran into some more specific problems. So what was our setup? Our setup was a geophysical fluid dynamics laboratory aquaplanet. This is sort of it's a pretty idealized model, but we decided it would be suitable for algorithm development. It's an aquaplanet, so no continents, just the basic physics of circulation and precipitation. So there's water coupled in. And this is a snapshot of the simulation of the sort of mid to northern latitudes that we're thinking about. We just choose a target location, and this is a snapshot of rain on any given day. Okay, so there's some storms these are extratropical cyclones, okay? And there's some storms that are near our target location. And if we look at a Hofmöller diagram, so time is increasing along the vertical and longitude in the horizontal, you see these streaks, which are little bursts of rainstorms, which are appearing and then propagating along with the waves of the atmosphere and then disappearing. The question is, how big of a storm can we make hit the target location? As you can see, some of the storms passed pretty close by, but didn't quite hit the location as hard. So could we apply perturbations to steer this storm over here, for example, and amplify it? So that's the question. So we applied stochastic perturbations to this model, a scheme called SPPT, which is used in numerical weather prediction. And what did we find? Well, we followed the AMS recipe, right, which says split the simulation when it crosses the threshold. So what happens when you do that? So the black dashed line is the ancestor, the original simulation. The solid line is the descendant. And this was the threshold that we're shooting for. So when it crosses the threshold, we apply a perturbation. And something very disappointing happens. The descendant does spread out from the ancestor, but only after the event has already passed by. We're not able to achieve a meaningful boost in the amplitude of this extreme event or a meaningfully different story. It's just a copy of it. So the effects of chaos, meaning the divergence, the growth of errors, is not taking place until after the event is over. All right, so it's not very useful in this case. So this is initially sort of a failure. Now, can anyone see an obvious solution to this? What remedy would someone apply?
Upstream, earlier upstream of the storm.
Okay, so apply something up. Well, would do what upstream?
Apply some enhancement or.
Yeah, I think that's a good physical idea. The thing is, if we apply it too late, like when the event is already here, no matter what the perturbation is, if it's small, which it should be, there's not really enough time for it to spread apart. So let me distill this into a cartoon. We had to make a modification to this algorithm. Okay, so this was the failure mode. We had the ancestor going through an extreme. We split off a descendant, but the descendant just makes a copy and doesn't spread out till too late. So the remedy is close to trying upstream. It's just trying early. Just apply the perturbation farther ahead in time, which leads us to our modified algorithm, TEAMS, trying early adaptive multi-level splitting, where if you apply some advanced split time, which we call delta, you are in fact able to achieve meaningful boosts. So this is like a really obvious idea. It sort of came out of ensemble boosting, but you have to make it mathematically rigorous because there's this other possibility: the descendant could be less extreme. It could be rejected. So you have to apply an acceptance rejection procedure. The mathematics eventually, it works out, and this, drawing on previous literature in engineering. But yes, indeed, if we time the perturbations correctly, so if we perturb this event before it happens, we get other versions of the event. But it doesn't always get a boost. So we apply the green perturbation at the green circle, we get the green event. And then we try to boost it again, we get the yellow event. It finds a new extreme event later on, and then we were able to boost this successively. So it's a little bit complicated, but by applying perturbations early, we can in fact modify and enhance the magnitude of these things. Okay. But the question is, how do we know when to perturb? What is that delta parameter? It's another parameter to tune. And an instinct that I get a lot is it's the Lyapunov timescale. Lyapunov timescale is the rate at which trajectories diverge, the exponential rate at which trajectories diverge. But this doesn't quite cut it because Lyapunov exponents deal with infinitesimal errors when the perturbed trajectory is very close to the unperturbed trajectory. But we're really aiming for finite amplitude boosts in the magnitude of the extreme event. So we need to go a little bit farther back in time beyond the Lyapunov timescale. And so it begins this mystery of how to find the optimal advanced split time. That'll be a running theme. But anyway, the main question is, do we get a speed up? Can we estimate these events more efficiently? And the answer is yes. And I need to walk through this plot to demonstrate why. So this plot is the vertical axis is the return level, how extreme the event got in millimeters per day when we're talking about rainfall. The horizontal is the return time, return period, or inverse probability, essentially the expected time between two occurrences of the event. And there's a few elements here. So the black dashed line is just the DNS, the control simulation, which is like our ground truth, which we ran from running a model for a very long time. All of the red lines are showing different runs of the team's algorithm, which is a random algorithm, so that you have to run it multiple times to and take their average to get statistics. And I know there's a lot of spread there, but there's also spread in DNS, so it's a little bit obscured here, sorry for that. But there's also a gray envelope here, which shows if we gave the same computational cost to direct numerical simulation, this would be the 50% error bar. And then what you can't see, unfortunately, very well is this red envelope, which extends beyond the gray envelope. That is taking the middle 50 percentile of the red lines. And so the thing to compare, the two things to compare in this plot is the gray envelope to the red envelope. All right, the lines are a little bit of a distraction. And the point is, with teams, with our algorithm, we can extend the simulation we can extend the estimated return periods by an order of magnitude. Sometimes more, sometimes less, depending on the specific settings. But we're able to estimate return periods of like 200 to 300 years using only 37 years of simulation. So that's like a somewhat small, that's like somewhat modest, but like it's an important speed up, you know. If you're trying to build the engineering projects for the dams and the bridges, et cetera, that will last for several hundred years, that will withstand the worst kind of events for several hundred years, you need to make estimates that are accurate for that long. And this is a more efficient way to do it. So that's the sort of basic result, basic minimal working example. Let me pause and ask if there are questions so far about the main idea.
Could you speak to the nature of the perturbation? I mean, you could do an advective boost or a
I've swept that deep. Yeah, that's right. There's many choices of how to do a perturbation. I've swept that detail under the rug a little bit, and that's a super important question, which I won't be able to address in detail in this talk, but like we'll point out is a very important direction of future research. In some cases, it might not matter, like for the sampling problem. Like it could be that whatever direction you excite ends up sort of rotating into the fastest growing mode, and it doesn't matter as much. But of course, when we think about like weather modification strategies, like what perturbation you make is determined by technology, et cetera. But like some perturbations will be more effective than others. That'll affect the time at which they should be applied, et cetera. I will basically say that's a wide open question. And designing optimal perturbations has many dimensions, and I'll be focusing on the timing dimension. But the ones I've shown so far here are using a specific stochastic parameterization where you force the simulation with a red noise process. And that's like standard practice in numerical weather prediction to drive ensembles apart to estimate uncertainty. But huge open question in general, yeah.
So it seems to me that if you looked at the adjoint operator for the vectors, you can figure out preferable directions and actually bias your random sampling to favor those instead of even generating those. Have people done that?
They're starting to work on that, and that's like one of the future directions I'll touch on in the end. But yes, it's.
I would have thought that would be like an automatic first step,
For a slightly complex reason, well, it is an obvious first step if the goal is to just maximize the amplitude of the event that we care about. But our goal here is not just getting the biggest possible event, but sampling the probability distribution properly. And so just maximizing does not get you statistics necessarily. So you have to be very careful about like how aggressively you shoot for the maximum. And I can certainly get more into this and how we designed the follow-up study. Yeah, but yes, we can definitely make use of adjoints, but we have to know what to optimize exactly. Yeah, please.
Kind of following up with that, this might be a dumb question, and ignorance for not studying the weather literature, but it seems to me like studying weather and climate, there should be a lot of like biasing distributions. So like rather than these splitting approaches, why not just go back to like importance sampling? Just like so good old fashioned, I'm just gonna like make the temperature hotter and then see how bad it gets and then correct for the bias that I introduced by making the temperature hotter.
Well, so I would say this is a form of importance sampling, like sequential importance sampling, et cetera. I would say the problem with just applying with broad strokes, like just make the temperature hotter, is I can take a snapshot of a day like today. I could automatically increase the temperature by 10 degrees, but then I would find myself in a physically inconsistent state. You can't just increase the temperature without implications on the speeds of the winds. Do you adjust the temperature up by 10 degrees everywhere in the atmosphere? Well, no, you should probably preserve the vertical gradient of temperature. Well, if you do that, you have to account for how the winds will respond and also how the moisture will respond. So like the whole universe of possible weather configurations is a nonlinear manifold where we can't just simply like increase one variable independently of the others. So like the only way to do importance sampling is, I would say, is in the space of small perturbations off the manifold, where we have to allow the weather to relax back into its natural, physically realistic configuration. And that's, I think, what splitting is all about. Does that make sense?
Yeah, I mean, it sounds like you're saying to me that, so the sims that I'm used to working with, we can create bizarro hellscapes and then normalize for those. But in those cases, we're confident that our hellscapes are physically realistic hellscapes.
Okay.
And it sounds like you're saying that if you were to just perturb the temperature, these models are so fragile that you'd get something that'd be fictitious, and the probabilities that you would get in that hell world would not simply be worse versions of this world. They would be, they'd be just artifacts of the model.
Yeah, and I wouldn't say it's the model's fault. It's nature's fault. There is no such like realistic weather state that exists if I just took today and I raised the temperature by 10 degrees. Yeah. But important question, and like there's ways to reconcile these ideas, I think. Yeah, really important, good questions. Any others before I move on? Okay, so this is the first demonstration that this type of thing can work. All right, but the operative question again is like there's lots of parameters to optimize. How do we choose the advanced split time? It came from a lot of empirical work here, but we used an advanced split time, or AST, of 10 days in this case, and we found that we calibrated that based on the rate of not the Lyapunov timescale, but the error saturation timescale of the model. So if we run a perturbed ensemble of simulations in red that are spreading out from the purple, and you run them forward, eventually the errors will grow exponentially, but then saturate and start to sort of wander independently around the manifold of weather states. And if you look at the time at which they reach 2/3 of that saturation value, we call that T 2/3, and empirically find that is a good heuristic for choosing the optimal advanced split time. Now, why do I have to tie it to the ensemble dispersion timescale? It's because if we change the resolution of the model from T21, which is a certain level of truncation in Fourier modes, basically, to T42, double the resolution. In fact, the optimal timescale decreases from 10 days to 4 days. And the reason is ensembles errors grow faster when the resolution is higher. So this is more of a model artifact that like representing the same physics with different resolutions changes how fast ensembles diverge. So we need to couple this algorithmic parameter of advanced split time to the ensemble dispersion timescale. And so this was also important validation, which we wrote up in this paper, which was just accepted in James last week, which is that teams can scale, or algorithms can scale to higher resolution, which is important for like shooting towards more complex models, provided a good rule for estimating this parameter of advanced split time. But we need such a rule. But then to bring it back to the physical picture, like what have we done here? If we look at an ancestor, an unperturbed event, versus its descendant, a perturbed event, what is the action of this perturbation? Well, we basically found a needle in a haystack perturbation to both shift and amplify the storm. So this is the snapshot on the day when the ancestor black line was at its peak. And then if I click forward by a day, or maybe it's 2 days, we find the day when the descendant is at its peak. And the descendant finds a more extreme peak, more extreme amplitude of rainfall, where the storm has both amplified, and also if you look at the difference, it's shifted. You know, the central locus of rain is shifted from one place to another. And so, you know, that was the effect of all these like Monte Carlo simulations. We just found that really effective perturbation. And you know, the idea of rare event sampling is, can we generate a large ensemble of these things and do a really detailed risk analysis with probabilities attached of the storylines at a reduced cost? That's the thing that we've been shooting for here. So we managed to do this, but at what cost? You know, the cost isn't only the final run. The cost is also tuning the parameters, tuning the advanced split time, and other things like the perturbation, you know, the type of perturbation and the size of perturbation, et cetera. And tuning these parameters, just like tuning a neural network in machine learning, is sort of a hidden cost and externality that I think impedes the broad scaling, useful scaling of these methods to like more real world problems. So that's an ongoing thing to contend with. And this is where I want to emphasize the critical importance of model hierarchies, you know, going back to simplified models to develop our best practices before applying them at scale to the more realistic models. Okay. And so I want to show you the backstage of this, which I think is the more interesting part, the backstage of this algorithm development of teams. Even that aquaplanet, this GCM, which I'm zooming in here to again, is showing the propagation of storms. This thing is still pretty expensive to run if you're trying to run thousands and thousands of experiments to estimate optimal parameters. This is still very expensive, and we needed to distill this problem into a simpler form where we could do more exhaustive, detailed experiments. So if we look at this, the essential problem here is that these events are moving. They're appearing and disappearing sort of fast, and they're moving past the location fast. So how can we distill this basic problem? Well, we found refuge in the prescience of Edward Lorenz, who came up with these various minimal models of spatiotemporal chaos. And he came up with a model in 1996, the Lorenz 96 model, with similar traveling waves, traveling chaotic waves, which have opposite phase and group velocities, et cetera. It's like a minimal model for spatiotemporal chaos. And we found that this model presented enough challenge in which to sharpen our algorithm. So it represents, you know, impressionistically some important features of the atmosphere, like advection, dissipation, and forcing. And what we found by doing a lot of exhaustive experiments is that if we tried out teams, our algorithm, with many different advanced split times, we found a particular optimum. You know, it's a minimum in that curve. And, you know, which depends on the level of stochastic forcing, et cetera. But the rule that we came up with in Lorenz 96 was the time until 3/8 of error saturation. And we actually had to adjust that to T 2/3 for the GCM. So this gave us some rough guidance, but it wasn't exact. So the model hierarchy helped, but what we really need is a more general understanding of what sets this optimal timing at which to perturb. And so a big question, it's some sort of emergent property, this optimal advanced split time. And the question is like, yeah, how do we go about finding it? What is it a property of? Is it a property of an algorithm? Like, the optimal depth of a neural network, or the optimal like step size, the optimal learning rate or something? Or is it something more intrinsic to the physics, to the dynamics? I'm rooting for the latter because I think it would tell us something more universal that we can apply more broadly at scale. But that's sort of the subject of this next part that I want to talk about. But I think it's an important question. What determines the optimal advanced split time in general? Not just for sampling and making faster estimates, but for weather intervention like strategies. How do you know when is the window of opportunity at which to kick the system to make it do what you want? It can behave non-trivially. But I think this goes to a bigger set of considerations. I think of them as dark clouds on the horizon, of these hyperparameters that we have to figure out. Thinking about making an impact on the world, per the ASU mantra, here's how I think of my role as it should fit into the risk analysis landscape. I think, there are lots of end users, stakeholders around the world, farmers, urban planners, energy system managers, who define the event of interest, define what disaster they're worried about. That's a task for the end user, like what variable, temperature, precipitation, flooding, what spatial region of interest, the time scale, and the model that we're using. That's a task for the end user. And we as as algorithm developers should respond by designing an algorithm that's effective with a good time horizon, a good advanced split time, and then other algorithmic parameters like ensemble size and killing and splitting rates. And if you're using AI, things like model weights. But in practice, and optimizing these parameters for each specific target, like each specific region that we're aiming the precipitation at, that gets really tedious. And if you have to do that afresh, welcome. If you have to do that separately for every kind of extreme event you consider, this sort of defeats the purpose of rare event sampling, which is to improve computational cost. So I find that in practice, so these are the dark clouds on the horizon. I find that in practice, my community of applied mathematicians, sometimes we go in reverse order. We just decide what problems are sort of doable that we can knock down with our tools, and then we define what the problem of interest is. And so then, like, we write our papers to give the speed ups that we can. And so I think there's a form of looking under the lamppost. And one example would be, it's a lot easier to think about long-lasting, large-scale heat waves or hot seasons rather than these like short, transient, local events. And it's not at all to pick on Valerio or Luccarini in his talk a couple weeks ago, but I guess that's more the regime he was focusing on, which obeys some sort of nice mathematical large deviation laws. And we're going at the opposite end of the spectrum, the short, local, and transient. All right, so how do we try to fix this problem? I don't have a complete set of answers, but I have two general approaches that I'm trying to follow. Two solution strategies. One is we want adaptive algorithms that can take in the features of a specific problem and sort of adjust on the fly its parameters. And again, put a premium on physical insight, hoping that advanced split time can be understood physically so that we can, carry it in our human brains and apply it much more broadly than like the idiosyncrasies of any particular application. All right, enough with the high level stuff, but like the game here is then in the quest for the optimal advanced split time and other parameters, what's the simplest model to illustrate all of the things it can depend on? So we started with the aquaplanet model over there, right? And it's a big three-dimensional model. The advanced split time could depend on a lot, like what location we're targeting and also what variable we're targeting. So I didn't show this, but we found different advanced optimal split times when boosting extreme temperature versus precipitation. So those are both like active tracers, things that are advected around by the flow. You know, we backed off to use Lorenz 96 to calibrate some best practices, but it's a lot less interesting of a landscape. There's not so many things that the advanced split time could depend on. There's only one set of variables. There's not like temperature and precipitation, for example. So this calls for something in between. And this is a more recent study that we've been working on, which I enjoy this test case a lot. It's two-dimensional turbulence, in particular, if you're familiar, quasi-geostrophic turbulence, where it's sort of a, it is 2D turbulence, but it's a model of the Earth's mid-latitudes, where you have like jet streams, you have two parallel jet streams, which are traveling from left to right. You have propagating waves. So those cyclones could be carrying precipitation, for example. It's a sort of toy model of the Earth's atmosphere, but it still has these transient properties. And furthermore, we can couple in tracers, but instead of having active tracers like temperature and precipitation that can change phase, we make it a passive tracer to just make the problem a bit easier, again, to step partially up towards this level of complexity. And so the background color is the value of a passive tracer, which is just being advected around by the winds. And so if we consider a specific location in this field, like a target city, we can plot a time trace of that tracer over time, and we find, you know, as per previous turbulence study, there's intermittency. There's occasional big spikes in this event, and then interspersed by more quiescent periods, but like sort of unpredictable big extremes. We found this to be a suitable test system that sort of has some physical content, but it's in between the super simple model and that super complex model, in which we can hone our tools better. And so to go through this a little bit more quickly, well, right, okay, so what we're shooting for, I won't go into all the details of this follow-up study, but I'm happy to chat about it more. Actually, let me pause. Are there any questions about the general motivation and setup for shooting for an in-between model? Or comments on anything so far? Please.
Passive
Tracer.
just circulating, or does it evolve and has it
Source and sinks? Yeah, good question. So pretty much in the interior of the flow, it's just circulating. It's just following along with the flow. There's no feedbacks. There's no phase change or latent heating, which of course you have in the GCM, because again, we're trying to distill the problem to its simplest possible form. So yeah, no feedbacks, but there are Dirichlet boundary conditions, 0 on the bottom and 1 on the top. It's, you know, to roughly mimic how in the Earth, you know, you have the solar insolation coming in at the equator and heat dissipating at the poles. That leads to a moisture gradient from the south to the north. So it's impressionistically follows some patterns that are present on Earth. But, you know, you can think of that as the source and the sink.
and
Yeah.
so this is now entirely dry.
Well, if you consider the tracer to be moisture, then I guess you can consider it like moist. But again, it's only partially so because there's no feedback of the moisture upon the dynamics. Like a way to make this a little bit more fancy would be to add in latent heating, which would make it similar to a study called by Lapeyre and Held, which found like there are really significant impacts on the dynamics when you add in latent heating. Like these vortices, these waves and vortices become much more skewed towards vortices, for example. Super interesting dynamics, but we're trying to develop algorithms and want to take it one step at a time. Yeah, and this type of system is also a favorite playground for machine learning emulation when people try to make data-driven models for turbulence. Anyway, I like this model a lot, but we're shooting toward a general criterion for what is setting this optimal time, this optimal advanced split time, and so hence the title of this preprint, which is just in revision at nonlinear processes in geophysics, boosting ensembles for statistics of tails at conditionally optimal advanced split times, or best coast. which we're trying to find. And so to illustrate the design here, it's like we're taking a pretty exhaustive approach where we have again an unperturbed simulation in black, an ancestor, and to try to figure out what is the optimal time at which to perturb this, and what does optimal even mean. We step back systematically in time steps of 2 days. So every 2 days we make a new ensemble of perturbations. Like so, here we make an ensemble of perturbations. We get the red bundle of curves. And as you see, they don't spread apart very much until after the event is already over. And then we step back farther in time. We make perturbations at each step. But back here, we make a perturbation ensemble, which leads to the yellow bundle of lines, which spread out a lot more. And then going much farther back, we get the blue bundle of curves, which spreads out even farther, but then doesn't reach as high of the extremes. And each of these stacks of dots shows, as a function of the time at which you make the perturbation, how extreme, like what is the resulting spread in the ensemble of extremes. Okay, this is a little bit of a complicated, gaudy spaghetti plot, but I think it captures the main thing we're trying to go for, which is there's some kind of intermediate range. There's some kind of cloud in here at which that's the window of opportunity. Somewhere in there is the window of opportunity to perturb when you get the right balance between replicating the extreme event that you started with, but also not going far, but also like forgetting just enough of it to make a diverse version of it without just regressing to the climatological mean. The question is, so that there's some kind of rough Goldilocks zone in there. But the question is what to optimize. So this goes back to Manu's question. It's not just that we want the most extreme event possible. We want both the most extreme and the most diverse ensemble of events possible. We need both of those things. And so, and the goal here is to optimally estimate the climate risk across an entire tail, not just the upper bound. Okay, so there's notions of probable maximum precipitation and things like this, but we're really going for the whole tail. And there's after a lot of empirical and hypothetical systematic exploration, we decided that there's a proxy metric called the thresholded entropy, which again, so entropy just to try to maximize the diversity of something, of a distribution, and thresholded to make sure that they're at least as extreme. Think of this like you're admitting students into a program. You know, you want them all to be at least some level of competent, but you also want them to have diverse backgrounds, like subject to that constraint, right? So given that, we designed an estimator, and we found that we did I should back up and say, in this study, we're not exactly putting this forward as a rare event algorithm that gets us a speed up, but rather we're systematically investigating an emergent parameter that comes out of rare event algorithms to just try to get a better sense of what sets that parameter. And I think we've made some headway onto that. And we find even without shooting directly for a speed up, we do get some speed up where if the vertical axis is the statistical error and the horizontal is the computational cost, roughly, this is our estimator, and this is what we get from an equal cost DNS. So it's not a full-fledged algorithm, but we're just trying to get a handle on the advanced split time. And physically, we can say this is about 2 to 3 eddy turnover timescales. I think understanding the full physics behind it is still ongoing, but the point of this is that this is measurable. I think this is more actionable to put into a rare event algorithm without having all of the expense of jointly tuning many hyperparameters at once. We can talk about more of the details, but okay. Any questions before I move towards a close on it?
I can do this at the end or now, but so it's more of a question comment than just a question.
Sure.
On this. Are you familiar with simulated annealing, metropolis hastings, or Hamiltonian Monte Carlo?
Yeah.
So my question then is, instead of looking for the optimal AST, I'm actually looking for the probability distribution of the AST in a given situation that meets all your criteria, right? Because you have a potential function you have kind of defined here. So
Interesting.
have you thought of it that way?
So a probability distribution over AST, I guess that's a whole other question because like the probability distribution that we're trying to estimate is that of the extremes, right?
I know, but
So-
you have a parameter, and I'm thinking as a Bayesian that there is a certain probability distribution of the AST that gives you the best answer on the metric of performance that you want. And since the AST changes with every variable and every situation, using a fixed value is essentially suboptimal. You want breeding there rather than just choosing a fixed value.
Yeah, yeah.
But then the minute you admit to that, then all your other hyperparameters go into the same scheme from the same point of view, and deriving the conditional distribution of the outcomes becomes very natural because now everything is in the entropy or probability space.
Sure. Yeah, that I haven't thought of it directly that way, but I think that could be useful. I mean,
So I'm actually in my head, I'm leapfrogging a bit more because you're coming up with the AI models next, because then I'm assuming my computations become faster.
right.
If my computation is faster, then that's not really the objective. The objective is the richness of the conditional PDF.
Right. Yeah, I don't have. Let's talk about this more. I have to roll it around, but yeah, right now I'm thinking of it. I guess a thing to emphasize about the optimal advanced split time is I put a C in front, conditionally optimal, and that refers to the fact that different initial conditions have different levels of predictability. And the idea is that like I've shown one particular event here that we've boosted, but other events, started from different states of the atmosphere which were more or less predictable. There's lots of studies about how like winter might be more predictable than summer. It's easier to make forecasts in winter than summer, for example, for some situations. And so if I chose another ancestor event, it might well be that I should perturb closer to the event or farther from the event. This specific shape of this curve of this like entropy as a function of advanced split time could change depending on which ancestor, which event we're looking at. And that's why it's important to have something that is adaptive to which event we're boosting. But the advantage of this is that as opposed to in like teams where you just set some global parameter, some single parameter that you must apply to all events, this allows it to adaptively adjust to the local conditions. So I think that's getting half a step towards what you're suggesting, Manu, which is that there's a distribution.
That's what made me think of it, frankly.
Yeah. But yeah, I mean, thinking of it explicitly stochastically would be another step. Anyway, it's just an example of an interesting optimal parameter, and there are other optimal parameters to consider. So, but zooming back out to the larger research landscape picture, I guess I've set up some dichotomies here between optimization and sampling and boosting. So this word boosting is coming back from the beginning of the presentation. This again is work from ETH Zurich, where they've been pursuing a research line on storylines, remember, so generating physical realizations that don't have probabilities attached. This is from a more recent one they did. Storylines for unprecedented heat waves. And the nice thing about ensemble boosting is it's simple and it's flexible. If you're some stakeholder in the world that cares about some particular local extreme, you can apply this pretty easily if you can run a model. Like you just make some perturbations and you run it. But they're not probabilistically meaningful. On the other hand, my team's paper with Paul tried to sort of set up a little bit of a friendly competition here, I guess. We said bringing statistics to storylines, So this gives rigorous probabilities, but as I have pointed out, it's sort of difficult and brittle to implement and tune the different parameters. But I think that in more recent iterations of both of these works, we've had some sort of convergence, some sort of meeting of the minds a little bit, where the ETH group has actually, in the last year, sort of in parallel, interestingly, with our work, has made actual probabilistic estimators on their boosting algorithms. This is still in sort of GCMs, I guess, with random perturbations. And we've done a similar thing in a more systematic, structured way on a toy model with structured perturbations, which I haven't exactly talked about, but we can more afterward. So ask me about that if you're interested. And ultimately, I think we're both recognizing the need for both of these things in tandem. the physics, the physical picture as well as the statistics. And the overall point to emphasize is that like multi-pronged research between different groups is really helpful for sharpening the tools, and we need to apply them in multiplicity to different levels of the hierarchy with different research teams. It's a very important thing. And to illustrate on a high level, the core dilemma is just sample versus optimize, right? If you have a simulation and you're running it, and you run it for some time, and you've hit some extreme, the question is, do I keep going in search of larger extremes, which will come after a long time, or do I recognize that I'm very close to one now if I just know which direction to perturb? And this will find me the tail statistics much more efficiently if I do that. So another way to say this is explore versus exploit. And if you're in the reinforcement learning, Bayesian optimization literature, this is a common way to frame things. Here's another way to look at it. Do we keep sort of simulating away, waiting passively for the biggest events to come and register, or do we make an active choice to dig in where we are? Do we keep exploring or keep exploiting? You can see the idea. And yeah, it's some balance, which we're still figuring out. And again, coming back to this question, we've really focused on optimizing the timing of the perturbation, but just because it's like a isolatable thing. But then the question is, what about the shape of the perturbation? Local versus global perturbations. Which one is better for estimating statistics versus what's achievable for weather control strategies? And so I want to just take a couple minutes at the end to talk about scaling up towards real world impact, which will involve all those questions, especially using AI. So there's a question maybe lots of people are thinking, which is, can AI models just solve our problems? And just by generating huge ensembles really cheaply, there's definitely some argument for that. Is this just a panacea? But some of my colleagues have done some very important work, I think, of looking at whether AI models can forecast extremes, because extremes are outside of distribution. And what they found is that a model, ForecastNet, which was trained holding out extreme tropical cyclones, could not forecast them. And that's a very important thing to notice. There's some generalizability across ocean basins, but not necessarily to more extremes. But on the bright side, if we couple together judiciously AI models and physics models in a rare event sampling pipeline, they can in fact help each other out. So this is colleagues' work, which I'm sort of joining and working on improving further. And then furthermore, again, to Manu's question about using gradients and adjoints, some scientists in Canada and Washington found that you can use the built-in derivatives of AI models to enhance the extremity of extremes. So that can be done, and it's exciting. But again, it's a little bit of a different question from, can we get the statistics right? And but furthermore, I guess there's still a question of, are these perturbations that they found physical? And the answer is probably sometimes yes and sometimes no. But to the larger point, these questions are all things the AI models are not directly trained to do. Forecast out a distribution, get the long-term statistics right, and respond physically to the perturbations. So all these things need to be rigorously checked, I would say maybe chaperoned by physics, as we build up trust in them, especially when we get around to controlling extremes. So that's like a really important set of considerations. And I think I've motivated some of the large-scale questions here, but just to summarize a couple ongoing collaborations and prospects that I have is, we've been working on with some other collaborators and students on applying these teams methods more broadly to different applications like extreme El Nino events. This was an undergraduate thesis, which turned into a paper, which I co-supervised, and working on extensions of this with other students at University of Chicago. There's also dual questions of, can we infer, like fundamental science questions of causality between different parts of the model system? By applying such algorithms, applying little nudges, can we infer the effect of one part of the system, like the stratosphere, on another part of the system, like the tropospheric extremes? So this is joint work which has just come out in a preprint, the SNAPSy project. Ask me more about that. There's always the prospect of coupling in AI to accelerate these things. And yeah, again, looking into the future, weather modification is, like Manu said, it's a similar game, same tools with related algorithms, but higher stakes. And there's different constraints, interesting constraints. And I think these things have to proceed in tandem because we have to assess the worst case scenarios associated with weather control, like pessimization is one of my advisors calls it. And we have to understand the physics in order to apply it with confidence and trustworthily. So, all right, so just to close, I think the most important thing here is to center human knowledge and human welfare in our application of sampling and AI methods. We should embrace AI, but for science, which is to help it, to help augment our own human understanding. Ask not only what the machines can learn, but what they can teach us. So I'm being a little bit sappy here, but I have a fondness for the aesthetics of science. I've done some outreach activities, which I always find very rewarding to sort of bring the science close to home for kids, for people across education. And we need to think of it in the same way about like leveraging technology and AI for always bringing it back to the fundamentals. I like to make a toy simulation of chaos of a seagull flaps its wings, and just using very simple computer codes, which I think are helpful for conveying in an educational setting, like how complexity can evolve. These are just interacting point vortices, which are advecting airplanes around. Just little playgrounds like this can be massively informative. And I'll leave with a couple of abstract pictures of a coast, which are closely related to that research project, but that's just a teaser. Ask me about it in conversation. I've talked your ear off enough, so I'll just end there and happy to take any questions and discuss further.